Again, thanks everybody for joining us today. We are very excited to talk about one of our newer products available within the Noraxon technology suite, integrated, into our multi-device setup, which is the Gateway 3D treadmill. Of course, the neat thing about it, and which we'll be discussing, is how this system allows 3D force and pressure to be captured together, representing the future of gait and running analysis. I'd like to thank my partners from HP Cosmos and Velamed for joining me today. Our speakers, first we'll have Dr. Bjorn Zimmerman. He is a sales and application specialist for HP Cosmos. Then we'll have Christian Lurch from Velamed. He is the senior sales manager there. And I will kick things off. I'm the product manager for Noraxon. And so I'll begin by discussing some of the aspects of the Gateway treadmill, including key features as well as some technical specs that we can review quickly before we jump into the case studies. So first, we'll take a look at the video here, which it is not playing. Let's give it one more try. So what you can see in this image is we have our 3D forces, which are captured from the Gateway system. And then again, we're able to also have that instrumented with a pressure deck. And so we can combine those two things to not only look at the peak forces, the braking forces, but then also gain some insight into how that foot is actually coming in contact with the ground. What are some of the roll-off characteristics? Where are the high pressure points? What does the foot rotation look like during the walking or running tasks? Some key features of this system are going to be that it has a single belt treadmill. So research has shown that for other instrumented treadmills that either have a side left and right split belt or a front and back split belt treadmill, that those will actually alter the gait patterns of the subject that is walking or running on them. In particular, I believe research has shown, I want to say it's Altman, that there was almost a 4 centimeter difference in the base of the gait during walking on a split belt treadmill compared to a single belt treadmill. So the single belt allows you to capture more of a natural gait pattern, including the kinematics, as well as the ability to look at those recurring foot strike patterns. As we saw in the image before, of course, the main advantage, a huge advantage of this system is going to be the integration of force and pressure, the option to at least. You can, of course, have one or the other, but with the Gateway system, you can integrate the two of them so that, again, we can analyze those vertical and braking forces while also getting high resolution center of pressure, understanding the foot angles and the roll-off characteristics as well. Another key feature would be the versatile integration. So being able to use this system not only in Noraxon's multi-device platform, but also through analog integration, being able to send the force and moment data into any motion analysis system. In addition to that, there's also the Arsalis software that the Gateway system runs natively on. And that includes our next key feature, which would be some different real-time biofeedback options. So you saw a little bit of that in the video or the live video that we were showing at the front of the webinar today. And that's also shown here in this image where we have the left and the right bar graphs here showing us any one of the gait parameters that we would like to display and have be utilized for biofeedback. very neat tool to be able to use that you're able to capture and have those calculated parameters be shown in real time to allow somebody to have an active training experience or active therapy experience. In addition to this type of biofeedback, there's also a very cool mode that the Gateway system can operate in, where it's a self-selected pace mode. And so that actually allows the subject to walk or run at a pace on the treadmill that's most comfortable to them without actually having to dial it up to a certain miles per hour, kilometers per hour setting. So based off of their step rate, and where they are positioned along the belt of the treadmill, that self-selected pace mode will actually change the speed to keep them in a certain zone on the belt of the treadmill. We'll talk a little bit more about the force and pressure here in a moment, but one thing I want to focus on next is going to be the single belt treadmill. And in particular, for gait, with a single belt treadmill, there is only, a single set of force curves or force data that's being measured from the load cells on the treadmill. Of course, during walking gait, actually as represented here in the image, there's a double stance. And so how do we resolve that? How do we decompose the force curve to show us an actual left and a right as opposed to just a total force curve or a forced measurement? Of course, this doesn't apply in running because there's flight and you're only on one foot at a time while running. But during walking, this certainly is something to understand a little bit better. Unfortunately, these have all been validated by research studies. One produced by Maurice et al. In 2016, where he validated the vertical force decomposition during double stance, both for normal gait and clinical gait. You can see here from the R-squared value that there's a significant strong correlation between the measured force and the computed force. In addition, very low error margins that you can see here from the relative error of 1.8% for normal gait and 2.5% for normal gait. As shown in the image, you can see how things are set up, right? So we've got our total force curve, which is shown here by this thin line, and then the separation between the 2 feet and where that decomposition would occur between heel strike and toe off, the start of double stance and the end of double stance for that one side. In addition, you can see that as well shown for the clinical gait down below. They went a step further and also validated the decomposition of the FX and FY measurements. And what I've got here is a plot of the median error for that shear force decomposition during double stance. And you're able to see that from the time percentage of double stance that there's very minimal error across the board for normal gait. Of course, for clinical gait, the error ranges extend a little bit further. And again, these are actually in measured units here. And in particular, where that the error increases the most is actually going to be at that peak double stance. So right in the middle, shown here in those graphs. So there is some error there, but they've been able to demonstrate still under I believe it's under a 7% error, relative error for the normal gait, and under a 10% error for the clinical gait for these shear forces here. This was a study produced by Bastian et al. Both of these published in Gait and Posture, the very well-known journal within our industry. So I mentioned that we'll be discussing the force and pressure features a little bit further. So what I wanted to do is highlight, some of the aspects that, having a pressure only setup would allow you to do, and then what a force only setup would allow you to do. So of course, 2 different sensor types and how they measure. The pressure system is a high resolution pressure distribution platform, so you can see how the foot is coming in contact with the ground. We're able to measure the center of pressure as it goes from foot to foot. Of course, we can see and do step detection even in double stance on this single platform based off of the shaping of the foot. We've got sample rates up to 300 hertz. The biggest difference, of course, between the two systems is what force measurements are available. And so for the pressure system, you only have vertical force, which is actually a calculated parameter based off of the amount of pressure that's applied to the platform. With the gateway system that operates with the load cells, and as you can see, by itself can be a much higher sample rate. We also have the FX and FY forces available, and so those can be seen, as you can see here in the graph, to be able to understand what those braking forces might look like in that transition from, in a heel strike to a midfoot and ultimately, pushing off with the toes. Both systems can be utilized to produce gait parameters. However, again, the pressure system adds a little bit of value where it's able to show us that foot rotation. We can see from the perspective of, a top-down perspective, what that foot rotation looks like. Is there internal and external rotation? And additionally, we can also break down the foot into zones so that we can understand certain roll-off characteristics or foot angulations, such as pronation or supination of the foot at contact, or where they might be pushing off on their foot when they go into toe off. So independently, these systems are both very valuable in what they can show you about the kinetics during gait, whether it's running or walking. However, together, they give you that next level of information that you're able to really break down all of the components of the kinetic makeup of the gait cycle. And within the Noraxon platform, we are the only system, the Gateway with the Zebras pressure platform is the only system available that utilizes these two measurements in one system. And so that is a unique aspect to our setup within the Noraxon software, and something that you won't find anywhere else. Quickly, we can go over some of the technical specs for this system, and in particular, looking at the running surfaces available for the Gateway system. So there's a 150 centimeter length, there's a 170 centimeter length running surface, and there's also a 190 centimeter length surface available as well. So very large treadmills, of course, manufactured by HB Cosmos, which they make some very high performance treadmill systems able to withstand high speeds as well as high loads, so you can do overspeed training if necessary, or you can have larger people on there as well without worrying about if the speed or the turnover of the motor is going to be affected. There's options to elevate the Gateway treadmill as well. You can see here there's a module which allows a fixed elevation to be achieved from 0 to 20%. Our load ranges on the sensors are 10 kilonewtons, so totally suitable for capturing running or walking. And then even an overload of 24 kilonewtons in case there's somebody running with a rucksack or something like that, or a very heavy person with a lot of force production. As you can see, the linearity and hysteresis are both quite good as well, both less than 1%. In particular, the FZ is significantly less than 1%. We've got minimal crosstalk also. And then the other thing that I would mention is just the sampling rate here. So integrated into the Noraxon system, we're capturing at 1,000 hertz, but again, by itself, the Gateway system can actually be dialed up if needed. All of these specs are available on the Noraxon website, as well as on the HB Cosmos website, and I believe on Velamed as well. Some of the target applications that we are seeking for this system are first going to be, of course, in the research realm, so looking at inverse dynamics and other measurements of locomotion and biomechanics. Being able to utilize the three-dimensional force data on a treadmill to get recurring steps and have that be utilized with a motion analysis system or an EMG system to be able to model how the different bone structures or joints are being affected by the forces that are produced during that walking or running gait. On the medical side, we've got standard gait analysis. We also have the option for therapy and retraining using the biofeedback options available within the system. And then we have our ergonomics, so being able to utilize the pressure mapping as well as the forces from the system to understand footwear design and assess how other aspects, maybe it's prosthesis, how those might be affecting the gait patterns for an individual. And then in the sports side, of course, running analysis and performance training. So, in addition to just looking at running parameters and different force parameters, such as the braking force or the peak forces that are achieved, the system can also be used in performance training, whether you're using the biofeedback options to adapt performance, or even integrating, a metabolic system to look at VO2 max testing. So that can all be integrated within the system to be able to capture that data and really deliver a high performance system. Within the sports realm, that brings us to our first case study, which I will hand over to Bjorn to discuss, and he'll go ahead and present that. One thing I would like to mention is any questions that we have during the presentation, please put them into the chat box or into the Q&A section, and we will actually be moderating those along the way, and then we'll have a Q&A breakout at the end of the second case study. All right, Bjorn, you are up, so go ahead and take it away. I will stop sharing my screen here.
Okay, so thank you, Zach. Thank you for the introduction. Hello from my side. My name is Bjorn Zimmermann. I'm the application specialist at HB Cosmos, and I'm happy to welcome you here. We have 96 attendees on the list, as it looks like. Yeah, as Zach told you, the Gateway 3D is a system that can be utilized for different applications, for different markets, different research topics. The Gateway 3D is not one system out of a box. It can be customized. It can be customized for your needs, whether it is in medical or in sports, ergonomics, shoe industry, whatsoever. So feel free to reach out to us to configure your system. Just to give you an example, for in the medical field, we can combine the gateway as a measurement unit. We can combine it with further systems such as our active gait correction system, the RoboWalk expanders, or the unweighting system, our Airwalk LT or Airwalk AP. So this unweighting system will work in conjunction with the gateway, but there will be no interference. So all the systems will be decoupled from the measurement unit, and therefore there will be no interference in terms of the high quality data. So I will start share my screen now, and we'll start my presentation. So I'd like to give you an overview or an example of how the measurement looks like in the system. As Zach already told you, the Gateway 3D comes with a separate software, its own software. a software for controlling the treadmill, for creating measurements, for set up clients or subjects, and all this can be recorded and processed in our software. But here and today we show you how it looks like if we transmit the data, if we transmit it to a third-party system. And in this case, this will be Noraxon software called MR3 with its unique features to integrate further systems such as EMG, IMU, high-speed camera, and whatsoever, different systems. So this will be seen in shortly. Our first case study will be a recreational runner. This is how it looks like in the software. You already have seen this, but I will show it in the software one more time, how it looks like. I will slow down the speed so you can follow. So we have the first example here. We have high-speed video. So now we're in slow motion. We see the runner, we see force vectors coming up, and we see a distinct heel strike running pattern. And we see here on this side the pressure plate, so we can really see how the roll-off, how the heel is touching the ground first and then having the roll-off later on. Here and on the left-hand side, for sure, we see the forces. So we not only see the vertical forces. I will stop that now here to continue the presentation. So we see the forces, and now I will explain everything that we see and some important facts that we see from the software. I excluded it. Just wanna avoid that you will be distracted. I will put some screens in my presentation here. So first of all, what could be seen here in this first case, in this example? So this runner displayed a big overstride. So that the speed was 10 kilometers per hour without any further instructions. Just run as normal as you like. And what we could observe is there was a big overstride. So that means the heel was touching the ground a few centimeters just in front of the trajectory of the center of mass. So just in front of the body. This is an observation we could easily see with the high-speed video. Okay, that's easy going so far. And furthermore, with the pressure distribution and the pressure distribution matrix, we could see how she was rolling off with the foot, with the feet. So touching the ground first with the heel, here more on the left-hand side, on the outer side. So this is the left foot. And then the whole forces on the rear foot, on the heel, will be transmitted or will be distributed over the whole heel, entering the midfoot zone, and then having the transition to the forefoot area and leaving the ground. So in push-off phase, leaving the ground for sure with the forefoot, with the toe area. So in this case, we see a clear heel strike movement pattern, and we see the heel to toe roll off. So touching the ground with the heel first, ending with the toe. So also from the pressure distribution, we could easily see the angle, so the internal or external rotation of the feet. And what could be seen here was like a normal angle, slightly external rotated, but that's a normal case. So there was no hard toe out pattern. So in some videos, we can easily see how someone is rotating the feet way too far and causing other problems like pronation in the transition phase and going to the push-off phase. But this was not an issue here. So this is the pressure distribution, but what we can also see is here, this is those are the ground reaction forces. From the ground reaction forces, we can easily see the highest magnitude, the highest value we reach with the vertical. This is the vertical load, the FZ direction, FZ direction. So the vertical loading is very high. And this total peak here, that equals easily and most of the time between 2 to 3 times of the body weight. So just consider your body weight is like 100 kilogram, and you have a single leg movement, single limb movement, so running, you're landing all the time with an average like 2.5 times of your body weight. That means that's a lot of impact every step. We can also see here, there's a very specific, I will go back, there's in running, especially for heel strike running, there's a very specific initial peak here. This initial slab, this is very characteristic for heel strike running. And this is a very important point here. We will come to that later. And this even here like equals about 1.5 times of the body weight in average. So those data is also coming from the literature, but it is represented here in this recording as well. To give you an estimation or a relationship, this is the vertical load, this is the anterior posterior, so the FY direction, the braking impulse, and for example here we are much smaller in the total amount and the total value. We are here in about 0.3 times the body weight. And as I said to you, when running a marathon or when running a 10-kilometer trial, a run, or when going out for 30 minutes run, you have several thousand single limb impacts per run. And if you could improve your running technique, maybe that will improve your health on the long hand, or could avoid any problems in the future. Because those high impacts create also high joint moments, and those are demanding for the muscles, for the tendons, for everything that is related to your mainly lower body and the spine. So if we exclude this vertical load, the vertical forces, just in particular here, I'm gonna spread this graph. So if we're gonna exclude it here, and we take that significant initial peak, we can also estimate, or we can calculate what we call the vertical loading rate. So vertical loading rate is a parameter that consists also of a time, of the timing. So how fast you increase the load. And this is a very steep impact here. It's a very high or very steep angle of that curve. And that in average equals about 65 to 75 times the body weight per second in average, but instantaneously, here like in the midsection, it could be like 75 to 85 times the body weight per second. So that's a lot. And the importance of that parameter, for just as an example of that parameter, there are more parameters with importance. The importance could be seen here in a research by Irene Davis about the loading rate. So she and co-workers could demonstrate that runners with a medically confirmed injury, they had higher average loading rates compared to those who never had been injured. So what you see here in the graph from this research is we have a rear foot striker. So heel was touching the ground first. We have here a midfoot striker and a forefoot striker. So, and according to the type of how you touch the ground first in running, rear foot, midfoot, forefoot, it will change the vertical load. So the angle of this of this initial parameter here. Very important. So they're talking about medical confirmed injuries. So what type of injuries could appear? It's mainly like the stress fractures. So for the tibia or the metatarsals, it could be also like plantar fasciitis, so on the bottom side of the feet, the infraarticular joint pain, mainly in the related joints here, so ankle, hip, knee, or even spine. Okay, so what factors, what is influencing the ground reaction force in running? So for example, as you could imagine, the shoe type is very important. So shoes offer cushioning. Shoes are offering damping. So if you run barefoot, there's almost no damping. So also barefoot running is completely different than shoe running. This can be easily seen and could be easily seen also here in a small case study with the software, for example. There are different shoes nowadays on the market, minimal shoes, so very close to barefoot shoes, shoes with cushioning, shoes offering stability like in pronation, and even motion control. So they control the type of how you pronate or not. So especially the shoe industry has many potentials and many could influence the behavior of the ground reaction forces a lot. So shoes on the market, if you go to a store and compare just the shoes, you see many things, many different things on a shoe, like the flare, which is like an outstanding angle or an extension of the sole. And the flare could be on the medial side, could be on the posterior side, on the dorsal side. And the rocker, or let's say the difference of height of the heel sole and the front compartment. So they have many pieces where they can change running style and where they can change the resulting ground reaction forces. So for sure also the overground influences the forces. So overground could be like damping. The Gateway 3D that you have seen in the initial video, in the live video, the Gateway 3D is a very rigid, very tough treadmill. It's very hard on it, so there is almost no cushioning, and this is for a purpose. We want to have a very hard treadmill, actually getting very close to concrete, because otherwise, if there is any damping in the treadmill, that is another factor that needs to be considered somehow. So we have the damping of the shoe, we have damping probably from the running technique, and if there is an unknown number of damping from the system, that would be not ideal. That's why our treadmill is very rigid. So we have concrete, we have tartan, so outdoor tracks, we have artificial turf, real grass, or even in terms of biomechanics, probably worst case, sprung floor, so classical sports hall floor, which is very bumpy, or can be very bumpy. Furthermore, the anatomy could change the running style and therefore also the ground reaction forces. So gender also matters. There's a difference between men and women in terms of the geometry about the hip, for example, or the center of mass location. And as you can see or read here, also body weight matters. So if I with 100 kilogram run on the treadmill, I will create forces, in total forces or absolute forces in Newton much higher than a lady of 60 kilogram. But the percentage of body weight will be about the same. So like if I'm running, it will be also between 2 to 3 times the body weight in maximum peak from the vertical load. So we have for sure also general anatomical variances like leg length or stability of the Achilles tendon, parameters like this. And for sure, the running technique. The running technique could be influenced by any pre-injury or some imbalances. That's for sure easy to understand. And as we could see, and we will go through that in the next case, also the foot strike is very important, and the foot strike matters, we can say. So therefore we come to the second case. The second case now will be a coached forefoot running style. So the same subject, just instructed to run on forefoot. This was just a verbal instruction. There was no training behind, no re-education. It was just a verbal comment. Now the next trial, please run on forefoot. How this looks like, we see in the next one. Okay. So if we just observe the video for the moment, we see landing on forefoot. That's a big difference. This can be seen from the video easily. We see the pressure distribution, how that behaves. We will go into detail in a second. And for sure on the left-hand side, again, we see the ground reaction forces. Okay. So coming back to the slides, I will explain everything that we see. So just by the verbal command, run on forefoot, or just by the coaching instruction, run on forefoot, we see a very different running style, and that will lead into a much less overstriding in this case. So overstriding or landing here on forefoot, and therefore overstriding is much below the body and much less of overstriding. This can be seen also in the pressure distribution. So this was the roll-off phase like what you have seen before, but now it looks completely different. We are landing here on the midfoot. The whole force and the whole pressure will be distributed around the same area. We're just literally entering the midfoot zone, but just a little. And then right before push-off or at push-off, we're increasing the total load until leaving the ground on the forefoot or on the toe, big toe again. So this can be seen very good from the pressure distribution matrix. So we have a forefoot pattern now, and in contrast, it was a roll-off heel to toe in the first trial. We have no heel contact, and actually that's it's a bit strange. So even midfoot runner or forefoot runner, they will sooner or later they will land on the whole foot, depending on the speed probably, but even like on average speed, they will touch the ground even with the heel. So even though they are forefoot runner, but this was like coming from the verbal instruction, run on the forefoot or land on forefoot. Yeah, but this could be easily seen from the software. From the ground reaction forces, there's also a very big difference now. So this is the heel foot or heel strike running pattern. And now there's a big difference. The curve looks much smoother now. There's no initial impact like this one here. There's no initial impact. So because when landing on the forefoot, the ankle acts as a damping system and therefore can absorb the initial shock. And therefore also the loading rate is much smaller now. What else can be seen here from the forces? It cannot be really seen, but also the cadence will change. Just by running on the forefoot, you have a slightly shorter stride length, and that will cause also a higher cadence, a higher step frequency. But we can go through that in the final report that can be seen over there. So as a summary, foot strike matters. As I told you, and as the research also has shown, foot strike matters. There is a big difference in the force characteristics and in the pressure characteristics when landing on the heel or when landing on forefoot. That makes a big difference, and there's a lot of research going on about this field. How can you avoid injury while running or when running over a long period of time? So we have seen less overstriding when landing on the forefoot, and that was also related to much lower loading rates. So how steep the angle, the initial angle of the vertical load was, and of course the pressure matrix changed a lot. So we could also see, but I've not demonstrated yet, we could also see some further alterations like the cadence I told you, but also kinematic parameters will change, and this could be seen with IMUs, so accelerometers, or videos, or even 3D motion capturing systems, or last but not least also the muscle activity, so the EMG signal could be altered or could be changed and could be observed even here in the same software, and this Christian will go over that in a few seconds. But before Christian will take over, I'd like to show you the report. So what I have shown to you here in my slides is just 2 clicks away in the software. You can easily compare dataset 1 with dataset 2. This could be done easily. Let me do this for you. Just quickly go through the report. So just within a few clicks, you will have the report of the direct comparison of 2 data sets. We have the pressure prints, we have the center of pressure diagram, the butterfly diagram, and related parameters from the gait line, for example. We have the running parameters according to Jekyll and Perry. We have spatiotemporal parameters, like I told you, step length. Just to show it to you, we have a longer step length here in running heel strike compared to forefoot running, so smaller step length, and that will lead, if the speed of the treadmill is the same, that will lead also here in an altered cadence. So we have a higher cadence in this example when running on forefoot. And of course, we also see here the forces, so anterior, posterior, braking impulse and propulsion. We see the vertical loading, and so those are average data, and we clearly see this is the heel strike, this is the initial slap, the very steep impact, and the very steep loading rate. And we see it also here in numbers. The maximum increase is much higher here, almost like double the value for this foot. Left foot, right foot comparison, and some further parameters, impact analysis. So the whole report can be customized. It can be like 50 pages long. It could be like 2 pages long, easy to customize. So thank you for the moment. I will be available for the Q&A section in the following, but now I'd like to hand over to Christian, and he will give some more insights.
Thank you, Björn. Thank you for letting me being part of that great webinar, and thanks to all the attendees for joining. I will present a little clinical case study that we recorded when we were testing the treadmill in August. And my presentation is on the musculoskeletal load assessment in level and incline walking after total hip replacement. First of all, I would like to introduce myself with a little video. Can I switch slides? So, okay, there we go. This is me trying to keep up pace with my girlfriend in our holiday in Austria in July while hiking uphill. I was regretting every beer and every Germknödel I had the night before. Yeah, and I thought that that video is a nice introduction to the topic. Well, the presentation is not about my holiday videos or holiday pictures. It's actually about hiking. Well, actually, it's about uphill walking and an increased musculoskeletal loading by doing uphill walking. This increased musculoskeletal loading could lead to an increased or to an ongoing neuromuscular fatigue. And this could give an insight if someone who is injured could actually go back to walking or hiking after an injury or after a surgery. And this leads me to the clinical case that we are having. We are talking about someone who had a total hip replacement. Fortunately enough, it wasn't me. I'm still good, but you never know what's coming. When we were planning for that webinar in Traunstein at the HP Cosmos headquarters, someone heard that we were going to test this specific setup, and it's a friend of an employee at HP Cosmos, and he had a total hip replacement. It's a male patient at the age of 43 years. He had a hip replacement on the left side. That was, when we met him, it was 7 months post-surgery, and the rehabilitation process was interrupted due to the Corona lockdown. Actually, the surgery was in January, and as you might know, in Germany, we had our lockdown by the middle end of March. So he had 4 to 6 weeks of rehabilitation after surgery, and then he couldn't see his PT for a while. The subject or the patient was subjectively feeling good when walking. He said everything was okay, but he wasn't sure if he could go back to hiking or even slow running. And okay, then we thought, let's do a little experiment. And we started with a very qualitative observation. You might want to look at that video. You see my colleague Kevin doing the measurement, and you see he's walking on the non-inclined treadmill. It looks a bit as if he's limping on the left side, which is the injured side, or the side after surgery. But in general, it looks okay, I think, from a qualitative perspective. But that's not enough, so we weren't happy with just doing that. Therefore, we had the following hypothesis. If we exposure the patient to an increased musculoskeletal loading, we would at some point introduce neuromuscular fatigue. And as we know from literature, neuromuscular fatigue is one of the reasons for overuse injuries. These overuse injuries over time could actually lead to things like hip replacement or major incidents like that. If we introduce this neuromuscular fatigue, it might reveal imbalances or impairments that we wouldn't be able to see when the subject is not fatigued or not loaded in an increased way. And therefore, we might get some insights into the musculoskeletal status of the subject, and might be able to find injury mechanisms, or even give some further information that is relevant for the rehabilitation process. So how did we do that in that case? We had the subject walking on the treadmill at a self-chosen speed for 5 minutes. In that case, it was 4 kilometers an hour. We had a baseline condition. That was the first minute, getting used to the treadmill. And after the first minute, we did a first capture. The remaining 4 minutes, we exposed the subject to an increased musculoskeletal loading by inclining the treadmill up to 10 degrees. And we were hoping to introduce neuromuscular fatigue to this increased loading. I remember Alex Berg's big chat comment in the beginning that we should stop having Alina doing uphill running. And this is basically what the idea was, to increase loading and introduce fatigue. During the whole time, we were recording 3D ground reaction forces, the plantar pressure distribution, electromyography, and kinematics. You can see after each minute, we took a recording of 20 steps, and therefore we had 5 recordings in total, 1 baseline and 4 loaded conditions, so to say. Everything was recorded in the Noraxon Myo research software. For the ones of you that are interested in the technical specs, you can see that we recorded the gaitway treadmill with 1000 Hertz, the kinematics with 100 Hertz, it's an IMU system, Noraxon Myo motion, and the EEG with 2000 Hertz. Let me give you a quick insight how. Oops. Okay, here I am again. This is how it looked in the software. You see a very busy screen. Looks a bit familiar, like the one that Björn showed. If the subject walks, you see 2 cameras for qualitative observation. We have EMG data here of gluteus medialis bilaterally, vastus medialis left and right, and vastus lateralis. We have lower extremity kinematics. See a lot of curves going on here. I will pick some out in a minute. And we have the ground reaction force. By looking at the ground reaction forces, you can already tell that there is a difference in the amount of in the force reaction peak, the FZ curves, the vertical ground reaction force. You could tell that directly. This is the incline walking in the 2nd minute. And I will show some data right away. I just want to show you how we got to the report. We used the reaction forces as events for the step determination, toe up, heel strike, and report. There we go. It's a bilateral gait report. And there it is. This is the report that you've seen from Björn. I don't want to go through all the details, but it's a classical gait report with temporal spatial gait parameters and the averaged ground reaction force curves, as well as the ankle, as the angles from the 3D kinematic system and the EMG. All right, please let me switch to my presentation again. Okay, here are some results that I picked out and I found quite remarkable. On the left side, you see the anterior posterior ground reaction force, it's Fy, and the vertical ground reaction force on the lower left side on the bottom. And on the right side, you see
Chris, real quick, we're only able to see the MR3 software right now.
Ah, okay. Can you see it now?
That's the presenter view.
Okay. One more try.
Yep.
Sorry for that.
And real quick, we appreciate everybody sticking around. I know we're running a little bit behind. We will be sending out a recording of the webinar to all of the attendees and registrants. So if you do need to jump off at any time, please feel free to do so. And you'll be able to review the remaining aspects of the presentation on your own time once you receive the recording.
Okay, thanks, Zach. I will speed it up a bit. Can you see my screen now?
Yep.
My presentation screen. Okay, you see this is the first minute on the left side and actually after the second minute on the right side. And it took only 1 minute to introduce a different loading pattern to the subject. We inclined the treadmill and you see after 1 minute there is a difference in the propulsion peak of almost 20%. And a difference in the FZ forces of about 9%. So the left peak, which is the injured side, is 9% lower than the right peak, and on the propulsion phase, it's the same. The left is lower than the non-injured side. So somehow the movement, the loading pattern changed during that two conditions, and we were actually hoping to increase that with over time, over the upcoming minutes. And as you see on the left side again is the incline after the first minute and the incline after minute 4. We still see some differences, but not as clear as between level walking and incline walking. So obviously the time we had in order to introduce neuromuscular fatigue was too short, and we couldn't really introduce neuromuscular fatigue. I was actually expecting to have a larger difference between the impaired and impaired side. This can also be seen in the footprints. On the top, you see level walking after 1 minute. On the bottom, you see the incline walking after 1 minute, and you see a clear difference in the side pattern. However, it has to be said that the maximum peak of the pressure is not different in both conditions. Well, it differs between the conditions, but not in a side difference. Looking at some kinematical data, you see that the range of motion for the hip abduction is quite limited on the left side. It's only about 7 degrees. So the subject or the patient tries to reduce the range of motion and introduce as less movement as possible, while on the right side he's having almost the double range of motion, and this can also be seen in the EMG. With the EMG, you see that the gluteus medialis has a higher average curve for the healthy side compared to the impaired side. Well, I don't want to interpret too much on the EMG, but I think it's somehow related to the abduction and the gluteus medialis. If we had only looked at the knee flexion, so at the sagittal plane, this is the knee flexion on the top left, and the dorsiflexion and plantar flexion on the left bottom, then okay, we would have seen some differences in the ankle joint, but not really in the knee and also not in the hip, which we actually expected. But looking at a different plane, in the frontal plane, then we obviously see some differences that we can also confirm in the ground reaction forces. So if we only had observed the sagittal plane, only by looking at this video, we wouldn't have seen any big differences. And as you can see, the 3 sagittal curves here, the hip flexion, the knee flexion, and ankle joint, there aren't too much of a difference in the curves except from the ankle joint. There seems to be some changes in the range of motion. However, we found it in the ground reaction forces. So can we confirm our hypothesis? We exposed the subject to an increased musculoskeletal loading. We could see that from the ground reaction force. We changed the loading pattern and shifted loading from right to left, no, left to right, to the non-injured side. Unfortunately, with the time, I think, was too short to introduce neuromuscular fatigue. We should have had the subject running on the treadmill or walking on the treadmill for a longer time. And he also reported it was kind of demanding for him, but he wasn't fatigued. Anyhow, we could reveal imbalances and impairments, and yeah, we can get some insight into the musculoskeletal status. So it's very obvious that after a very short time, with only changing the musculoskeletal loading in walking, we get a different musculoskeletal loading status. And that might also give insights on the process of the rehabilitation process that should still go on. Okay, coming back to our subject, should he go back to hiking? After that little test, I'm not a therapist, but rather a biomechanist, I would say he should rather restart rehabilitation and focus on the muscular imbalances around the hip, especially in the frontal plane. And he should get some observation during the rehab process in order to follow up with rehab progress. If he would be able to also do some testing with inverse dynamics, that would allow for looking into joint moments and joint loading, that would also be very interesting, but in that case we do that. And now I'm concluding. So ergometer fatigue tests are very well established in cardiovascular diagnostics. Sorry for that typo here. It's for the last 20 to 30 years, it's very, very common that if you do a cardiovascular diagnostic, that you go on an ergometer and will be fatigued by the people who are doing the diagnostic. And I'm really questioning why this is not a standard in the musculoskeletal biomechanical diagnostic. Coming to my last slide, I would like to focus your attention on my YouTube link. It's our YouTube channel, MoCap Lab. It's a channel about biomechanics and motion capture. We do interviews with biomechanists and motion capture users, and yeah, it's all about biomechanics. Okay, yeah, looking at that iceberg, I'd like to start a discussion with the hypothesis that our standard, if it's static or even dynamic musculoskeletal assessment with non-fatigued patients or subjects only allows for a very, very small insight into what's actually going on under the hood. But if we start to expose our subjects to an increased musculoskeletal loading and introduce neuromuscular fatigue, by doing that, we will have more insights and reveal imbalances and impairments. Yeah, this is basically what I believe. I hope this is going to happen. Thanks a lot, and I hand over to Zach.
Wonderful.